Yes, I'm start recording here. This is density lab experiment 3. Experiment, let me have a little bit more bold format of the pen here. So, experiment number 3, density. This is a little bit different from the density we did last time with the measurement with verniers. Remember the stainless steel balls? Those are different from what we are doing today. Today we will be doing the density of some liquids and some solids, okay? And some of them are in powdery way, some of them in a metallic way, correct? So first of all, before we go further in describing the density, we have to know the formula of density. So the density is a ratio, and you will see in chemistry and physics we are dealing with a lot of ratios. So density is ratio of the mass over the volume, and depending on the state of the matter itself, then we can have 3 different units for the density. So units depend on the status of matter, correct? So what are those status? So if we have liquid, if we have solids, so then we have the units are, or the unit is gram per centimeter cube, or sometimes called gram cc, cubic centimeter. Cubic what? Centimeter. So if we have liquids, then we have the units is used gram for the mass. As you see, the mass does not change, always in grams, and here is milliliter. If we have gases, then the unit will be gram per liter, correct? So we have for solids gram cubic centimeter, for liquids gram per milliliter, and for gases gram per liter. So one more thing we have to know about these units is the relationship between the C, oh, that's large here, between the cubic centimeter and ml. It turns out this unit here, 1 centimeter, cubic centimeter here, 1. It does not want to write. Well, let's take it here. Here, guys, this is 1 centimeter cube. Centimeter cube or cubic centimeter, correct? So this is the same thing. It means that if I have a cube, its dimensions 1 by 1 by 1, height, length, and width or depth is each one is 1 centimeter. The volume of it will be 1 centimeter cube, which will be filled exactly with 1 ml. That's what it says. So 1 cubic centimeter or 1 cc is equal 1 milliliter, correct? Now sometimes we don't have the way to express this one here. Well, that's what we have to do. We don't have a pipette that will pipette for us exactly 1 ml. So we do approximation, an estimation of this, 20 drops of the eyedropper or the pipette, the plastic pipettes you have in the drawer. 20 drops is equal 1 milliliter or equal 1 cc, 1 cubic centimeter. Correct, guys? So whenever we want to measure 1 milliliter and we don't have the way to measure it, we don't have automatic pipettes or something like this, we can still use estimation 20 drops with the eyedropper, correct? By eyedropper, by the eyedropper or the plastic dropper you have it in your drawer. So that's the one. Now the second one, what is the dependence on density on temperature and pressure? It looks like the density is highly dependent on the temperature and on the pressure. So if you change the pressure, if you change the temperature, the density will change, correct? Can I take this one out now? Everybody has this? Everybody has this? So I'm taking this one out and look at the unit, at the density, which is dependence on temperature and pressure. So density D, now I just equal mass over the volume, and the dependence is always temperature and pressure. Well, it turns out to be the temperature is the most important condition. That's because the atmospheric pressure or the pressure is hardly to be changed like the temperature, correct? So temperature is the most important condition, correct? And therefore the temperature will have a big effect on temperature. So the pressure all the time, we measure the temperature is always 1 atmospheric pressure. So therefore we keep it here, is kept constant at the value of 1 atm, 1 atmospheric pressure. So we don't really tend to change the pressure, but we change the temperature a lot in our labs depending on the condition. Therefore this formula has to be really reflecting the importance of this condition. We write D, density, subscript T, capital T, that's the temperature, and this is mass over volume. So that's the correct way to express the importance of the density dependence on temperature. This is very important condition. If you change temperature, the density will change. You can look for example H2O table from 0 centigrade Celsius to 100 centigrade Celsius. The density is not the same, different densities, different temperature. But the pressure is very hard to change. We keep it all the time at density is measured at 1 atmospheric pressure. Everybody is following? So that's the two condition is affecting. Now with this here, that's the main formula, correct? Or this is the main formula here. Can I make 2 out of this? If this is the main formula, this is main formula. Can I make extra 2 sub-formulas out of this? Can I? Yes, I can, correct? So yes, I can. So let's do so I can make the mass, correct, equal to, what's the mass will be? Density multiplied by the volume. This is the from here. So I'm going from here to here, and I'm going from here to the second one. Volume is, correct, mass over density, subscript of T. This is the second formula. So I have 2 formulas together, 2 formulas to sub-formulas from the main formula. So if I have the density, the ratio between mass and volume, I can determine with the help of density and volume the mass, or I can determine the volume with the help of mass and density, correct? So one more last thing here we have to look is the density is extensive property of the matter or intensive property of the matter. So can I take this one out? Everybody has it? Everybody has it? Okay, so let's take it out. And the question is, the last question we have to go through here, is density intensive or extensive property? So, is density, D subscript of T, temperature is very important, because if you don't classify the temperature, then your value of the density is not correct. Is not correct. Really, is not correct, because the density is very sensitive for the temperature. So, and I think if we look at the, we don't have here a thermometer, but we have in the other lab. I think the density here in the lab temperature is the other lab. It will be the same lab, because density will be around. I have to check it.
Oh, you didn't check it now?
No, I got it today.
Oh.
Yeah. Email was there. Yeah.
So do I need to check it before you check it? I need to check it now?
You have to check it.
Or can I give it to you now?
Yes.
I need to make sure that it has been charged and the value
Yes.
there.
Yes. Thank you. So, the lab temperature is about 22 degrees Celsius. Sorry about this. We are checking the microphone. Luckily, I got the microphone, but I don't know if it's charged or not. Same thing when you get a phone, you don't know if it's charged or not, so you have to check it. So I have no time to check it. So, but anyway, our lab supervisor will check it for me. So the temperature is 22 degrees. So when you write a density, please write subscript of 22 degrees Celsius. The subscript. That's you are classified as you have taken the measurement of the density in this specified temperature. Are you following me here? Some textbook, they don't really, they go just easy on this. That's not easy, because look at the density in each literature in the web or any textbook. They have to have it in what? They have to have it in the related to temperature. So today you have to write the subscript of what? 22 degrees centigrade Celsius. That's the lab temperature. So is the density delta D subscript T extensive or intensive? Physical property of the matter. What do you think, guys? Somebody will help me with this, answering this question.
Intensive.
We covered that last week? No? Yes? Yes, we did cover. We said the density is always intensive. Density, the answer here, let's put this one another color. So here another color. Density here is always intensive. Physical property of the matter itself, correct? What we mean by intensive, meaning does not depend on the amount. If I can measure 1 drop of any liquid, correct? Like today you'll have the opportunity to look into those, or trillions of that liquid, the density should not change. So meaning intensive means it does not depend on the amount of matter. On the amount of what? Of matter, guys. Okay, guys, any questions so far? Any question? Any question? No question? Okay. Let's take this one out and look at the file we have, the procedure. So the procedure here, just to show you what we have to do. We have 2 solids. Here guys, look at this. Can you can look into this. So well, let me see here. Control P. I'm not check. Yeah, this duplicate. You should be able to look into the whole thing. So it's duplicate. That's camera is working, and the screen monitor is working too. So we have two solids. That's a metal here, and I can tell from the structure of it that the color is cylindrical shape, and looks to me like a copper. Okay, if you look, maybe look at it. Give it to the camera here a little bit. Can you see it? That looks to me 28E, the sample, but looks to me like copper. This one here, looks like shots, small tiny shots. Okay, small tiny shot. You can use them as a gun shots, but they are a little bit crooked. It's not spherical. They can be used, and the name of them in chemistry is shots, because you can use them as really in the gun itself. So what do you think this might be? Well, from looking at those shots as a chemist, eyeballing, if I have no experience, I can take them out and then keep them in my hand, see what if they are dense, will be very heavy, correct? Might be lead, might be iron, correct? Might be magnesium. But let me take one and see if they are really, if I can determine well, here it is, one of them here. Can you see it? You can see it here. So the camera here, a little bit, they are light and grayish, so most probably they will be around aluminum, that density of aluminum. So, but just eyeball this, just eyeball the structure, I mean the texture and the structure of this cylinder here. Tell me that's a copper. And these shots here, you can use them as aluminum because they are light. If I have one is lead or copper or gold, those are heavier in density, correct? So, okay guys, that's the two solids here. First, what we have to do, the density of two solids. One is irregular, one is regular, correct? We'll not do all of them regular, or we'll not do all of them irregular. No, we'll do one of them what? Irregular. We'll not do two. Maybe your procedure says two. No, just one. This one here, these shots, which I suspect is aluminum. I give you the answer up front. I want you not to have the answer, but the main thing is you have the skills of doing the actual experiment. And this looks from the texture of the cylinder, this is a copper. This is a regular one. It has dimensions, correct? So we'll do with different displacement method, and we can do dimension, but we don't have a vernier, I think, today. But we can do displacement for both and determine their density. So next is we'll have the density of the way they are written. This is very confusing for you, but that's what we want. One irregular shots, one regular cylinder. Regular shape is cylinder, irregular are shots. I suspect the irregular is aluminum. You can't tell me it's wrong or right. Aluminum is a density of 2.7, correct? And the copper is around 8.9, so roughly about 9, correct? And aluminum roughly around 3, correct? 3 gram per ml, or 3 gram, those solids, gram per centimeter cube. Now the next here we have sand and sodium chloride. Their names are there, are posted, so there's no secret. We know that's sand. We know this is what? That is sodium chloride, kitchen salt. And this is sand, silicon dioxide, NaCl. NaCl and SiO2. SiO2, silicon dioxide. So we have to determine the density of both. Correct, guys? Density of what? Of both. Here, those metals we have, the regular metal and irregular metal, we'll do by displacement. But this one here, we have to be careful because those crystals, they have a lot of air in between the particles. That will give us an error inside density determination. Are you following me here? So we'll have another method, not the method we did for the two metals, type of metals here. The regular one is copper cylinder, and the shots are aluminum. Okay, that's what I suspect. But this is sodium chloride. We don't know what the density of it. We don't know what the density of this. However, both they have, the problem is they have a lot of air pockets through the crystals. We don't see those pockets, but there's a lot of air pockets in between, and that will give us an error inside measurement of our density. We have to eliminate. So let's go for determining 4 items, correct? And we will do okay, so we will do those here in 2 liquids. We can use the tap water to determine their density, as well as we will do what? Ethanol. We'll see what's the density in ethanol, what's the density in tap water. Are you following me here? Are you following me here? So, and it says that we have to do an unknown A. I don't think so. We'll have the time to do those all 1, 2, 3, 4 for density. If we have time, we will do unknown A. Correct? You know how to do this unknown A? I need the density of this unknown. Somebody will tell me how to do it. This is unknown A. So let me here go and look how we do it. We'll not do. That's the easiest one. I need to start with the difficult one, which is the regular, irregular metals, and the sand and salt. This is the easy one. We'll leave it to the last, if the time permits, because that's about 4 densities you have to determine today. 4. That's the 5th. But if the time permits, yes. If the time does not permit, no. So how we do this? Somebody will tell me? Well, that's easy, correct? So I take a graduate cylinder here. Just show you this here. Unknown A. Unknown A liquid. So density. So what you will do? Take a graduate cylinder, correct? You weigh the graduate cylinder empty. Weigh empty. This is graduate cylinder. Weigh it empty, correct? And then use use what? Use the graduate cylinder to measure exactly 10 mils. How much? 10 mils of this graduate cylinder. The graduate cylinder may be up to 25 mils, correct? From reach zero here to 25 mils. So the maximum capacity of graduate cylinder is 25 mils. So I will add 10 mils to this. So here it is. Add 10 mils. So suppose here 10 mils somewhere. That's the unknown. I have to read it with 2 digits after the decimal. Say suppose 10, 10.00, or I might do some 9.80. So whatever is, it has to be straight to 2. If you don't have any number after the decimal, 2 zeros. We have to read 2 digits after the decimal. So now I know the volume. I know the volume of the unknown. I know the weight of the graduate cylinder empty. I go and reweigh the whole thing filled. Reweigh the whole filled graduate cylinder. Correct? Now, the difference in weighing will give me the mass of what? the mass of the 10 moles, correct? I put in the graduate cylinder, correct? And the volume is 10 or whatever, 10.8, whatever the number, close to 10. But I have to know the exact amount of it. Mass over the volume will give me what? The density. That's the easiest one. That's I would recommend we'll put it at the end. If the time permits, we'll do it. If the time not permits, not do it. This is not challenging. The challenge here is the those two metals, the metals as a shot here, shots, and this metal here as cylinder. Those are the challenging part. And the most even one, difficult one, because of the air pockets, is the as you can see, it's the sand and the sodium chloride. So let's go and look at, can I take this one out? As I said, the unknown A, skip this one for the time being. Don't do it. Do it if you have if the time permits. If the time is not, because that's a lot. I don't know why they put about 5 or 6 or 10 densities, because and each one you have two trials to see your results correct or not correct. I think that's more than one lab. This is more than one lab. That's 2 labs in one, because time consuming, because you have to make sure that you have the right results. You have to do it 2 trials, and then you have to do it twice, and then you have to verify this value, where is it in the literature. So if you get about close to 3, you have go and look at the web, which element metal is about 3, close to 3, that's aluminum, correct? Which is around 9, that's copper, correct? That's the issue I have with the time. The time is not really good for this. So procedure, unknown 2, even they give you 2 unknown, my goodness, that's about 6 or 7 densities. That's impossible to finish them with really a very decent data you can get. You'll be running out of time. So we will do just one at the end. So just follow me here. We'll do here, keep at end of lab, and if time permits, do only A, unknown A. You will do A if the time permits. So skip this one here for the time being, because you cannot do A and B, each one 2 trials, and then you do the solids, the copper solid cylinder, and the shots, aluminum shots. You cannot do that. That's 2 trials, and then you have to do the sand and the sodium chloride. That's very challenging. So okay, so we will do the 2 solids. Okay guys, can I take this one out? Everybody has it? So skip the procedure for the 2 liquid unknowns for the time being. If the time permits, we'll do it. If the time does not permit us to do it, then skip it. We'll not add it inside our data, inside our lab report. Everybody agrees? And if you look at this, you can come here and you just keep this one when you submit to this lab report, your data here. You look at the tables. The data has to be in your tables here. This is the unknown sheet. See here, those are. You can skip this page here. If you have no time to do this page here will be out. If we have no time, are you following me here? And I doubt that you will have time for that, because you have to do 2 trials. See here, those are trial 1, trial 2, and 2 unknown liquids. I don't think so, unless you are running fast, and your data are not correct. So this one here, just skip it. Don't add it to your data inside your lab report, correct? So any question about this? Let's go for the solid, the solids here. We have aluminum shots, and we have cylindrical copper shape. So let's do here. What is the procedure here? So we'll determine the whole thing. So with the graduate cylinder, you have to pipette the burette is here. You can use the burette and the pipette. So what you will do here, you will use a graduate, again graduate cylinder, and you will have, correct, the two solids unknown. It said one regular shape, so I gave you those shapes here, guys. Just follow whatever I'm saying to you, and that's what you'll have. Cylinder here, and some of them look like copper, some of them look like aluminum. I don't know, but that's a cylinder here. So you will do by displacement method their densities, okay, to trial. So you will have a graduate cylinder here, so that's a cylinder, and then we have, those are shots, and most probably they are aluminum. I'm not sure, but you'll figure it out if I'm correct, unless they have different shots there. So different shots, aluminum beside whatever, lead. You can tell if they are heavy. They have to be something lead or copper. Or copper is very easy because it has distinct color. So how we do this, unknown. Well, it turns out to be, you fill, that's your graduate cylinder here, again, correct guys? So first of all, you take the metal itself out here, guys. You will weigh the metal on the analytical balance. Nothing on it, nothing. You weigh this one, correct? So the first step is weigh the metal cylinder by itself, correct? And then you'll add 10 mils here. That's your 0 here. This is 10 mils. 10 mil, and this is the 25. That's the graduate cylinder 25. You can bet your amount, exact amount, which is 10.0000 mil, using the burette. You can add the 10 mils. Here it is, your burette. That's your burette here. You'll add exactly 10 mils. 10 mils. Correct? So I know the mass, guys, correct? And this is called displacement method. I know the mass. So I know the mass of this copper. Then I will come back and do the same thing for the shots. So here is the mass. I know the mass. Yes?
It says 50 mils of water.
It does not matter.
It doesn't matter?
It does not matter. The main thing, I have to know how much I have added. I can add 15 mils, and we don't want to be close. The graduate cylinder is 25. The closer you are from the 25, the least precise your data. So 15, 10, that's good. But don't go lower 5. Don't go beyond the 20 or beyond the 15. So 10 mils is good. Okay, so 10 mils would be ideal. That's almost half, close to half. So so then you'll add there. So but the metal is not inserted yet, correct? So you weigh the metal itself. I know the mass of it, correct? Then I use the burettes here. I'll show you how to use the burettes there, and you'll measure the how much? 25 mils. That will be your what? Initial volume. That will be what? Initial volume. Take the burette out. Take the burette out. Take it out. Then when you add 10 mils, then tilt this one here 45 degrees. So I'm tilting this one here 45 degrees. Why I'm tilting this one 45 degrees? I don't want to lose some of the H2O, some of the tab where I added, so it will splash out. Correct? It will splash what? Out. Now you can use a distilled H2O, but tab water is the same thing, has no effect. Whether you use distilled H2O or tab H2O is not affecting in any way or shape. Why is not affecting tab if you use tab or H2O? Well, it turns out distilled will be H2O, has no cations, no ions, correct? The distilled one has no ions. The tab water from the faucet here has a lot of ions, but they don't react or don't entertain any chemical reaction with the metal. Whenever we are measuring a density, our measurement focus on no reaction with the object. No reaction. Anytime I use the liquid I use should not react with what? With the metal here. So 45 degrees, then I will insert the metal here, correct? Insert it there. Then I straighten up the graduate cylinder here, make it straight. Then I read how much is now. That will be my final. Correct? Everybody is following? That will be my final, because it will be not 10 mils. It will be what? When I dump this heavy metal cylinder here, it will displace H2O. The tablet will be displaced up. That will be my final. I inserted exactly 10 mils with the help of the burette. So that's the difference will be give me the volume. So for the difference, so density at 22 degrees for this metal here, I think I suspect, as I said, is copper. So the mass is from direct weighing. I weigh the mass, and the volume is final minus initial. This is the mass of this. Okay, in the procedure does not tell you where to go. I want you to go to the web, look up, or I can send you, look up what that metal is. I can put for you some metals there, so you can tell me which one is this. So anything about this? Anything about this? Now, we can do the same thing with this one here, correct? So you'll fill the graduate cylinder after you are done with everything. Fill it with the burette with what? 10 mils, not 15. I mean, it's up to you. 15. The main thing, you don't go below 5 and below 10. Will not go below above 20. That's where the problems with the precision, with the redemption, repeating your data will be. The precision will be less. So 10 mils of distilled or tap, it does not really matter, because both of them, they don't react with these shots, with I think aluminum shots. You will tell me if I'm correct, or they might have something else there, another type of shots. I don't know. I picked the lighter one. That's aluminum, I think. My suspicion. So now, instead of this, before I'm dumping the shots, I have to weigh. Okay. Well, it says I can weigh whatever I like, between 5 and 10 grams. I'll take my just enough to replace. If you take a small amount of these shots, what will happen, guys? What will happen? The amount of displaced H2O will be least. You cannot read very well, correct? So I will take, so at least between 5 grams should be good, 5-6 grams, and put them inside. But if you put like 3, 4, 5 of these shots, your density is not correct, because the mass is not enough to displace H2O, the tabor we are using. Okay, so use about maybe 5 grams of this, weigh 5 grams, and then use the burette to put 10 mils in graduate cylinder, correct? Everybody's following? So then when you are done with the 10 mils inside, tilt it and put all the shots at once, correct? And try to shake what? Try to shake this, because those shots they have some air pockets. Try to shake a graduate cylinder before you are reading the final volume, correct? And the mass of those shots divided by final minus initial, their volume will give you the density. Any question about this? That's displacement method. We'll do just the displacement method. We'll not do vernier to measure the cylinder dimension, the radius, like we did before last experiment, or determine the height or the length of the cylinder. No. And even this is very difficult, because the shots are not sphere. They are crooked. They are really crooked spheres. There's not a really sphere per se. So that's those are the two ones. Everybody's following? Everybody's following? So here they are. Can I go further? That's for the two solids. That's for the two solids. and I can come later on and look at the data here. As I said, the first one, A and B, just skip them for the time being. I'll come here, the solid unknown, the regular one, that's the cylinder one, the copper or whatever they have, aluminum, whatever. They have different cylinders, but those are the regular shape. Those are regular shape, those are, the shapes are cylinder. So cylinders, they are over there. So write the ID number, whatever the ID number for copper, it says 28E, 28, can you see it? It says 28E. Write the number of it, weight, the mass, then the initial volume when you insert from the burette, 10 mils. I mean, from my point you can add 15, but don't add above 15, and don't add below 5, below 10, below 20, yeah. So, but you have to know the exact reading how much. Then when you insert this cylinder here, it will be a final, it will be displaced, copper will be displaced, then you can write how much is the final. The step D minus step C will give you the volume of the solid, the volume of the cylinder, and the volume of the shot in the second one, correct? So then the density will be B over mass over E. B mass over E. Can you see that? So now this one here for the irregular shape, those are the crooked spheres. The crooked, I call them crooked spheres. As you can see, they are not per se spheres. They are really crooked spheres. But if they are made spheres, they can be used by hunting guns, whatever. They are not deadly. Those are not deadly. The aluminum, they are light, therefore not deadly. The real shots, they are heavy. So they can be made with copper, lead, those very heavy. So irregular shape, those are shots, and my suspicion is aluminum. You can verify my, and they have a name here. They said solid unknown 2. Solid unknown 2, that's their ID. Solid unknown 2, that's irregular shots. You do then the same thing we did the solid in the top here. So this one here, I can add, so this one here, this one for the cylinder here, and those are here, those are the shots, correct? So now we'll go for the most challenging part, because it has air pocket in between. We'll go for sand and for sodium chloride. How we'll determine those in two different liquids, in ethanol and in H2O, correct? So let's look at, can I take this one out? So here it is. We'll go for sand and H2O. So determine the density of salt. Okay, we talked about displacement method. So now we are here. Now we are where? We are here. So let's look at what we can do with the sand and what we can salt. We'll start with the salt. So what you will do with the salt? Somebody will tell me, without looking, without reading, what's the best way to do it? With the sample? Okay, that's correct. But we'll do it the same like displacement method, correct? Everybody following? So I will take a graduate cylinder. That's my graduate cylinder.